All right, so today we're going to talk about two new topics in the second half of the first unit. Both kind of pertain to what we discussed last week with percentiles and z-scores. So cumulative relative frequencies are basically going to be a graph of our percentiles. And then when we calculate things like z-scores, when we're looking at those positional measures, we're transforming our data, which is shifting and rescaling, which we'll kind of discuss as we go through today's notes here. And so the first thing we're going to start off with is cumulative relative frequency. And so there's quite a bit to kind of unpack here on this first slide. But what we're looking at when we talk about cumulative relative frequency, okay, is we're looking at a display of our percentiles, essentially. And so when we talk about cumulative relative frequency, we're kind of talking about like a running total of our percentiles as we go through our distribution. So as we look at the table here, there's a lot going on. So we're just going to kind of break this down a little bit. In this first column, this is something we've already discussed. This first column here is just a frequency table. So we're looking at the age of the first 44 presidents and when they were inaugurated. So 2 of the presidents had been inaugurated by the age of between 40 and 44. 7 presidents were inaugurated when they were at an age of 45 to 49, and so on. So this is just keeping track of how many presidents were inaugurated within a given range of ages there. And then in the second column, again, something we've already discussed before, but now we're just looking at relative frequencies. So we're looking at 2 of the 44 presidents, or 4.5%, were inaugurated between the ages of 40 and 44. 7 of the 44, or 15.9%, were inaugurated between the ages of 45 and 49, and so on. So it's just the same stuff we talked about in the first half of the unit. It's just how many people, or how many individuals in this case, were in each class that we created. And then we would create things like a histogram or a relative frequency histogram based off of that. Now, cumulative frequency, so that's what this third column here is. Like we said, for cumulative frequency, we're looking at a running total. So what we're saying here is as I go from one class to the next, I'm looking at how many total individuals I've encountered to that point. So within my first class of 40 to 44 years of age, 2 of the presidents had been inaugurated by that point. And then when I go to 45 to 49, in our frequency table, we said that 7 of the presidents were inaugurated within that age range. But on our cumulative relative frequency, we're keeping track of the total number up to that point. So 9 of the presidents had been inaugurated by the age of 49. And then when I go to my next class, 13 more presidents were inaugurated between 50 and 54 years of age. But for us, on cumulative frequency then, we're looking at 22 total presidents have been inaugurated before the age or at the age of 54 or earlier. So it's just keeping track of a running total. How many individuals up to that point have been accounted for. And so then when we convert that into that cumulative relative frequency, in this last column, it's just a running total of what percent of values we've encountered up to that point. So in that first class, 4.5% of the presidents were inaugurated by the age of 44. Then in the second class, we added another 15.9%. So that means by the time we get to 49 years of age, 20.5% total of our presidents had been inaugurated by that point. And then we add another almost 30% to that. We get the 50th percentile there. So 50% of the presidents had been inaugurated by the age of 54, and so on. So what we're really calculating here with these percentages in my cumulative relative frequency is we're calculating kind of our percentiles. We're saying at this point, there's this many or this percent of our values at or below this particular class. And so when we look at the graph on the right then, all that graph is just showing us or displaying what we get from our cumulative relative frequency table. So starting at 40 years of age, well, it was our 0th percentile, but between 40 and 45, we got 4.5% of the presidents accounted for. So we increased from 0 to 4.5% in that first interval. And then from 45 to 50, we increased by another 15.9%. So that gives us a total of 20.5%. So we increased 15.9%, but at 50 years old, we're at that 20.5%. And then from 50 to 55, we added another almost 30% to get to 50, and so on. And so we just keep track of how much we add to each interval until we get to our 100th percentile. So once we've accounted for our entire set of data or individuals. So that's kind of what this is looking at. Now, the way we use it then is specifically for percentiles. So as I look at this graph, the y-axis goes from 0 to 100%, and that's going to keep track of the percentiles in our data set. So if they asked us, for instance, to find the 30th percentile, so what age for presidents would approximately represent that 30th percentile? So I would go to 30% on my y-axis, or as close to 30% as I can here. So I go to about 30%, and then I follow that across to the graph, and then I follow it straight down. And so what I would say is the 30th percentile then appears to be about that 52 years of age. So if I had a president that was 52 years old when they were inaugurated, they would represent approximately the 30th percentile of our data set. Or they might say this particular president was inaugurated when they were 64 years old. And so they want to know what percentile would that represent. So if I do 64, this time I'm starting on the x-axis because I'm looking at the actual age. So starting at 64, I would trace up to my graph. So I just draw my straight line straight up to where my graph would be. And then I trace over to my percentage. And so 64 years of age would roughly represent, we'd say, about the 90th percentile. So we're just looking at where those values go along that x and y axis. So if I want the 64-year-old president, would be about the 90th percentile, or if I'm converting from a percentage to a value, the 30th percentile would roughly represent 52 years of age. So I can do anything with those different percentiles. Probably most importantly, as far as this cumulative relative frequency graph is concerned, is I can find important parts of my data set like my quartiles and my median. And so as we're looking at this, the median represents the 50th percentile. So if I go to 50% on my y-axis and I trace across and down, 55 years of age would roughly measure my median in this case, or my 50th percentile. So that 55 years of age would represent my median age at inauguration. Or if I wanted my quartiles, my quartile 3 would be about 75%. So if I go to about 75% on my y-axis and I trace straight across, and then I trace straight down, we'd find that about 59 years of age would represent that quartile 3, that 75th percentile. Or for my quartile 1, which would be the 25th percentile, so I go to about 25%, trace across to my graph, and then trace straight down, and we find that that quartile 1 would be approximated by about 51 years of age. So I can calculate any percentile from this cumulative relative frequency graph, so I can approximate by just drawing my line straight across and finding the appropriate location, or given a value, converting it back to a percentage. And then if I wanted things like IQR, I could take my quartile 3 minus my quartile 1, in this case an IQR of about 8 years of age. So that's kind of how we're going to deal with those. And so for the most part, it's either going to be take your percentage, convert to a value, or take your value and convert to a percentage, all of which can just be found by tracing from one spot to another on the graph there. Okay. So then that takes care of the cumulative relative frequency. As far as shifting data, so this is where our transformations come in. So when we take our data set and we transform it in some way, it means we're either adding or subtracting a constant amount. That's what shifting would represent. or we're changing units, or we're doing something where we're multiplying or dividing, which is what we're going to call rescaling. And so when we shift our data set, okay, what we're talking about is if we take our numbers and we add or subtract a constant to every single value. So let's say I measured the length of a certain group of individuals in centimeters, we'll say. And what happens is after I measure all the individuals in centimeters, I noticed that I accidentally measured too much. So I measured everything 2 centimeters longer than it was supposed to be. I misread the ruler, whatever the case may be. So as I'm looking at these 5 numbers, I'm just making these really easy and basic to try to illustrate what we're talking about with this shifting. But we notice then that for my data set, my median would be about 14. My IQR would be 4. And then my range, so min and max, would be about 8. So we can calculate our summary statistics, our medians, IQRs, means, standard deviations, things like that. But as I mentioned then, I messed up and I misread the ruler. And so I had everything 2 centimeters longer than they were supposed to be. So really, that 10 centimeter individual should be 8, the 12 centimeters should be 10, and so on all the way through my data set. So everything needs to be subtracted by a value of 2. Now what that does then is all of my positional measures get moved. It's like I took the entire distribution and I moved it to a new location on the x-axis. So what happens is every one of my positional measures decreased by exactly 2 centimeters. So median went down to 12, quartile 3 went down to 14, quartile 1 went down to 10. So all my values, all my positional measures decreased by that same amount that I subtracted. And so what we see up in the statements here is measures of position will change. That's your means, medians, quartiles, anything that we're measuring as far as position is concerned. And they change by the exact amount we added or subtracted from the data set. But if I notice my spread, in this case, like we calculated IQR, so if I look at my spread, notice I'm going from 14 to 10, so Q3 minus Q1 still gives me the same measure we had before. So the IQR didn't change. My standard deviation wouldn't change because my values didn't get further apart or closer together when I shifted. I just took the entire distribution, picked it up, moved it to a new spot, and that was it. So my positional measures will change, but as far as my measures of spread, they will not change in any way, shape, or form. So subtracting 2, adding 10, whatever the case may be, positionally will change everything, but spreads will remain constant. So IQR, standard deviation, remain unaffected. So another way of illustrating this, if we look at the following 2 distributions, what they're looking at here is first weights of men. So they just grabbed a random group of men, they measured their weights in kilograms, and they got the following distribution there on the left. And then they took those same men and they converted their weights to the kilograms above the recommended weight. So basically they figured out what the recommended weight would be for this group of individuals. They took each of the original weights minus the recommended weight and looked at the differences in the weights there. And so what we notice is the only thing that's really changed, so the only thing that's actually happened here is we've taken our distribution and we've moved it to a new location on the x-axis. So where my median would have been in like this 70 to 80 range probably, now it's at like the -4 to 6 range over here. And so what's happening is our medians shifted, our quartiles would have shifted, our min and max have shifted, but as far as spread is concerned, nothing will have been affected by this adding or subtracting in this case. And I see that the shapes are exactly identical, the variability is exactly the same. So everything that has to do with measures of spread remained unaffected by that shift. And so that's one of the things we have to be aware of, is if we add or subtract constants, positions will change, spread will remain unaffected. Now, if we rescale our data set, so let's go back to, we'll just use the same 5 numbers we had before. So again, we have a median at about 14, quartile 3, quartile 1. We got our min and max all there, right? So we have this original data set, but let's say this time I messed up and I want to double everything. So whatever the case was, I had this original set of data. Now we're going to double all the values. So now my 10 becomes a 24 or 20. My 12 becomes a 24, right? And so I shift all my, or I rescale all my values. So everything gets doubled. Now, as we look at this then, we notice that just like before, median increases in this case because we multiplied everything by 2, and it increases by an actual factor of 2. So the median doubled in size, quartile 3 doubled in size, quartile 1 doubled in size, and so on. So all of my positional measures would double. Same thing with mean and things like that. But whereas shifting the data before really only affected those measures of position, now we note that when I take like IQR here, my original IQR had a measure of 4. When I took the data set and I doubled it, all of my values became more spread out. In this case, now I have an IQR of 8 instead. So when I actually rescale the data, when I multiply or divide by a constant, I'm going to change everything by that same factor. So measures of center, measures of spread, everything gets increased or decreased by the same amount in that particular case. So I doubled all my values. That means I double all my positions. I double all my measures of spread and get the new values from there. And so again, just to kind of illustrate that, when I rescale, so again, taking the weights of males in kilograms, so that's what's here on the left side, so the weights of men in kilograms, but let's say this time I want to convert those kilograms into pounds. So that's what's over here on the right side. So what would happen is we'd have to make our conversion. In this case, we'd be multiplying everything by the conversion from kilograms to pounds. And so what we notice is, as far as the distribution is concerned, the shape is pretty much the same. They're both skewed to the right. We both see or can see outliers or possible outliers in the upper end of this. But the things we notice is not only has our position changed, so now our median has changed and moved on the x-axis, but we also notice that our spread has changed as well. The second graph is more variable than the first after having converted, after having rescaled the data. So we can see how not only do the measures of position change, but also spread whenever I do my conversion using multiplication or division. And so then the last thing here is just a quick example, kind of putting all this together then. So when I do my transformations, if it's a shift, a rescale, or if I do both, kind of how do we attack that situation? So a company selling clothing on the internet reports that its packages have a median weight of 68 ounces, and we have a IQR of 40. So as we're looking at that then, what's happening is if they take those packages and instead of just shipping the clothing, they're going to put a flyer in with it. So a sales flyer or whatever the case may be. And so the flyer weighs 4 ounces, and they're going to do that in each package. So what's going to happen is they're adding 4 ounces to all of their original packages. And so what would happen is my new median, by picking up the data and shifting it to a new location, my new median would become the 68 original ounces plus the 4 we're adding to everything, so 72. But as far as the new IQR, because that's a measure of spread and all I did was add a constant to everything, that remains unaffected by that shift. So even though we added 4 ounces to every package, the IQR is still going to be 40 ounces. Now, if I take that new data, so now I have these new packages with the extra flyers in them, and instead of measuring in instead of measuring in ounces, I want to measure in pounds. Now I'm putting a rescale on my data set. And so what's going to happen is I'm going to be taking all of my values and I'm going to be dividing by 16 as we see the conversion here. So if I'm dividing everything by 16 to convert it into pounds, that means my new median, which was 72, now gets divided by 16 and becomes about 4.5 pounds. And then with this rescale, that means I'm also going to be changing my measures of spread, and by the exact amount that I multiply or divide by. So in this case, I divided by 16. So I would take my original IQR divided by 16, and we get a new IQR of 2.5 pounds. So as we're looking at these shifting and rescaling, we have to make sure that anytime we're doing any sort of addition, we're going to change our measures of position, but spread remains unaffected. If I were to multiply or divide, everything gets affected by that exact same amount. And if I have a combination, like in this problem, the adding and subtracting and the multiplication division will affect the median, mean, quartiles, things like that. But the adding, subtracting does not affect the measures of spread like IQR, standard deviation, whereas the multiplication and division will. So just knowing when to apply each to those particular measures is going to be the key. And then so from there, you should be able to attack the homework for tonight and then try these out, answer key coming in tomorrow. And then if you have questions on anything, you're always free to ask.